Recording.
Okay. So today we will discuss the notion of rigid monoidal category. So rigid monoidal category. So it's a particular class of monoidal category in which every element has a left and right dual. So a monoidal category is called rigid if every object admit a left and a right dual object. And today we will focus on this notion of dual object. So what is a dual object? Definition. So an object X star in a monoidal category C. So let's call the monoidal category C is called a left dual of X of an object X if there are in fact two morphisms one called evaluation from X star tensor X to 1 called evaluation morphism and the co-evaluation, which is a dual so from 1 to X tensor X star. So you should be careful. For the evaluation map, you have the star here on the right. The X star is on the left of the tensor product, and for the co-evaluation, it's on the right here of the tensor product. Okay, so called co-evaluation morphism. Evaluation and co-evaluation morphism. Satisfying such that the following composition are identities. So you have a kind of commuting diagram for morphism to be evaluation or co-evaluation. So I will write the axiom for being evaluation and co-evaluation, but before I put some space here. It's not for nothing. I will write how so pictorially how we can write. So maybe I will take a color in red like that. So picture for this morphism. So f x, so it's a morphism. So it's denoted from like that. So from x star, you take x star and you go to 1. And this is denoted, so pictorially, the picture is like that. So you draw a picture like that. You go from x, and you go here, x star in the other side. So it's like you have only one x, and the one is deleted. So this is the evaluation map, like that. And the co-evaluation map is denoted pictorially in the same way. So it's from 1 to x here, x star, and it's denoted, so notation, this is just a notation. Notation. So you should write notation. There is a notion for 2 point equal, like that. Like that. So this is a notation for the evaluation and the co-evaluation morphism. And you note, as I said, that we don't consider, we remove the picture for the morphism 1, for the object 1, as the identity of 1. So you have like that, or like that, and we remove the 1. OK. Ah. Et maintenant? Quelqu'un qui a écrit, c'est ça? Non, c'est moi qui ai entendu. Ah, non, c'est bon. OK. So 2 pictures. Picture for the co-evaluation and co-evaluation map. OK. So this is maybe I should write. So these pictures are not in the book, but I think it's relevant to. It's quite usual. These pictures are very well known in the literature, so you should know how to interpret pictorially this evaluation and co-evaluation map. So now, what about the axiom for being an evaluation and co-evaluation map? So I will write what is a formal axiom, and then I will also rewrite it in pictorially, and you will see that pictorially the axiom is very, very intuitive. So the following axiom, so you have this composition. So you start from x. So remember that so x, this is identified to 1 tensor x always. So you can apply co-evaluation to 1 and identity to x, and you get x tensor x star tensor x. And then you apply the associativity constraint x star x. So you just move the parenthesis. And finally, you apply the identity of X and the evaluation map. And you get X, which is X tensor 1. So you have this map to 1. Okay. So this composition, so from X to X, and another one from I don't know. So this composition from X to X and another one from X star to X star will be assumed to be identity. So from X star to X star, you have the similar. So this is X star tensor 1. So identity of X star tensor co-evaluation of X. What you get is X star tensor X tensor X star. And then you apply the inverse of the associativity constraint. And you get X star tensor X tensor X star. And finally, evaluation X tensor identity of X star. And you get X star. So, one tensor X. So the following two compositions are identity morphism. So this is, you compose, this composition is just the identity, and this is also just the identity by definition of what is a co-evaluation and evaluation map. Now, what about pictorially? So pictorially, this composition are as follow. So the first one first. So again, this is not in the book. So I will write in blue. Okay. So you start from X. So pictorially, you start from X. You have an X. And then you have a 1 also, but you don't write 1. So I put it in a like that. And then you apply co-evaluation. So I am doing this, I am doing the first. You apply the co-evaluation. So you have co-evaluation. So as it is written here, the co-evaluation is just like that. So you have X. So you, okay, and then you apply the associativity. So you have this one and this one together, and you have this one. This is together, and this one, and you apply the associativity, but the associativity constraint is not can be. You don't need to write it pictorially because of the Maclaurin coherence theorem. Everything is fine. So then you apply the associativity constraint. So, and then you have the identity here and the evaluation map here. And so this draw like that. X. So so here this is associativity. Let's see. Oh. Like that. I will write another color for associativity. Associativity. Okay. So this is coev x here. So I will write how to write that better. So here it's coev x. Here it's evaluation x. Okay, x here. And so what this first action is saying? This is saying that this is nothing but only the identity. So you start. So this is identity of x. This is x. So you start from x here, and you go from x here. This x, and this should be identity. So identity, draw like that, just only one line. So topologically, this is saying that you have something like that, and you can deform it into something like that. You can just like that. Okay. Let's make it better. Okay. So this is called zigzag or snake equation. So there is a name for that. So zigzag or snake equation. So this is for the first, and for the second one, for the second identity. You have the same picture but symmetric. So you have and you have something similar. So here it's evaluation x, coev x. Here it's x star. Identity of x star. It's x star. So you should x star. I don't know how to draw it. Okay. So this corresponds to the second one. Okay. So be careful. Be careful. For example, here, so you can decompose in the definition. Here, you have you apply 1, 2, 3 morphism. So you have also the first one here, and the third one here. So 1, 1, 2, 3. 1, 1, 2, 3. And yeah. Okay. So okay. If you want to make, for example, here this is x, but here it's x star. should be careful. Even if something this is drawing like that, this corresponds to you have x star here and x here, doing like that. This is just a notation, so you should not be confused. Okay. So so finally we remove that. We don't. Maybe I just draw it like that, but with another color maybe. Can draw like that also. This is one, and so you don't put it. Okay. So you see, so this two axiom for being an evaluation co-evaluation is very intuitive. You just deform topologically this picture into a simpler one. Okay. This is a way to define a left dual, and now we can similarly define the notion of right dual. So I will go quicker. The right dual is the same, but we need to fix the notation. So idem for right dual definition. An object X right dual, so you put the star on the left like that. In C is called a right dual of X again, evaluation and co-evaluation morphism, but with a small variation. So we have f prime x tensor x like that. One. So and co-ev from 1 to x prime x not x prime x x dual. So maybe I say x prime before. It's not x prime, it's x dual. So x left dual before and now right dual. X star, yeah. Star x. And again, you have a picture. So the picture pictures. So here it's like that. So you have x star 1. So it is you make a picture like that. Now x, you see, this is in the other side. Now for the evaluation map, you have the x going from left to right. Here you have x going from right. Here x is going from right to left. And same for the co-evaluation map. You start from 1 and you go there. So it's x star x, and this you draw it like that. Again, on the, with x in the other side. So these pictures are just notation. As I said, these pictures are not in the book. But I think this is good for intuition. And again, you have the same axiom. So the same two composition, analogous two composition should be identity. So cof prime x tensor x star x associativity x star x star x and f prime x tensor identity of x. So such that so these two compositions are identity. So cof prime x tensor identity of star x. So again, you always have the. So I did not draw, but you should understand x here as x tensor 1, etc., etc. Here you should understand as 1 tensor star x. Always the same point. So here, so this is star x tensor x tensor star x. The associativity constraint star x star x, like that. Tensor x tensor star x and identity star x tensor evaluation prime x, and you have x star x. Okay, such that our identity again morphism. Okay, and so the picture again similar. So let's draw quickly the picture for that. Picture. So you have something like that. Like that. So here you have f prime x co f prime x. Yeah, you start from x, you go to x, identity of x. Here you have co f prime x, f prime x, and you start from star x to star x, and this is identity of star x. Okay. Again, you have the three step, the co-evaluation, the associativity, and the evaluation. Co-evaluation, associativity, evaluation. Okay. Maybe I should go something. No, it's okay. 3. Okay. What about now? So we have a notion of left dual and right dual. And what is the relation between the two? So we can prove something easy. So remark. We will prove this remark. If X star is a left dual of X, then X is a right dual of X star. In other words, in other words, you can take star of X star equal X. So proof. So proof. So the proof is immediate. So take, as I said, star of X star to be X. So you take it. So you assume you want this to be the right dual of X star. Like that. And take f primed of X star to be the evaluation of X, and co-f prime of X star to be the co-evaluation of X. Then we need to check that those two compositions are identities. So I will write the first and the second will be same. So you start from X star, you have identity of X star, tensor co-evaluation prime of X star. X star tensor. So star X star. I will not write the second one, which is same. It's just this is trivial, just to fix how things are working. And I will have no enough space. Tensor X star, and so I need to put this on the left. And evaluation prime. So by definition, you need this one to be identity. And also the second one, I will not draw. So we need to check, and also the one from X. To X star, to X. There, so we need to check that this I identity, but they reformulate by definition, by their definition, by the definition here, all this definition. So the definition of that, that, and that as so X star. So identity of X star, tensor coef prime of X star. The coef prime of X star, this is coef of X. Coef X. x star tensor. Again, this one is x by definition. So x tensor x star. So you apply the associativity x star x star. So x star tensor x star. And again, the evaluation prime of x is evaluation of x. F x tensor, identity of x star, and the other one. So which are, so the other one, place, which are exactly, which are identity by, which are identities by definition of the fact that x star is a left dual. So this is trivial. A left dual of x. So this is trivial. If x star is a left dual of x, you can take the right dual of x star to be, you can take x, and it's okay. This is one right dual. So we will see later that the left and right dual are unique up to isomorphism. But before that, okay. So similarly, you have the same. So idem. If star x is the right dual of x, then you can, so then x is a left dual of star x. In other words, you can take the star of star x to be like that. So the proof is the same. And so again, another remark. The dual of 1 is equal to the left dual of 1 is equal to the right dual of 1 is equal to 1. So you use, so by convention, 1 tensor 1 equal 1. Just take Ev and co-Ev to be identity. And if you don't want to use a convention in the so without convention, but this is too much. Without convention, just take iota or iota inverse. So what we call iota inverse is the definition of a monoidal category. This is a unit structure or something like that. But yeah, we will not use this. We will use the convention. So like that. Okay. So this is okay for the unit. The dual of a unit is itself 5 minutes before the pause. So so proposition. If X is an object of a monoidal category, as a left respectively right. Maybe I missed something. Oh, yeah. Sorry, I don't want to state this proposition now. I missed one page. So this proposition says that if an object has a left respectively right dual object, then it is unique up to a unique isomorphism, preserving evaluation and co-evaluation map. But before stating and proving this proposition, I want to motivate the notion of right and left dual. Coming from, so the motivation comes from the notion of left and right adjoint of a function. So I am completely lost. 24. Okay. So what about? So again, this is a part will be added from the book. It's not in the book. Added part. Left and right adjoint of a functor, and we will see the relation between the notion of left adjoint and the notion of left dual, left and right adjoint of a functor. So the idea is that the left and right adjoint will be a particular case of left and right dual applied to the category of endofunctor of a category. The monoidal category of endofunctor of a category. So you have the monoidal category of endofunctor of a category, and the left and right dual there will be exactly the left and right adjoint of the category. But what is the left and right adjoint of a category, of a functor? Of a functor. So we will define that after the pause. So pause. So this is a pause. Okay, so let's restart. So what about notion of left and right adjoint of a functor? Left and right adjoint of a functor. So let C and D be two categories, not necessarily monoidal, but locally small. So we fixed at the beginning that every category is assumed to be locally small here, which means OM is a set. You have OM set. So consider two functors f from D to C, G from C to D, such that for all x object of C, y object of D, the OM set of f of y x is in bijection in a specific way we will explain after, of y g of x, where the bijection is natural in the following sense, where is natural in the following sense. For all so in the following sense. So there are natural isomorphism. There are natural isomorphism alpha x, beta y, such that so you have the functor. So this functor f x from D to set. The functor taking an element of D, an object of D. So you need an object of D, you will put here, and what you get is a OM set, so it's a set. And so this functor, there is a natural isomorphism called alpha x to this functor OMS D of something gx, again from D to set, and the same for the source from C to set. Like that, and you have the same for OM C f y something from C to set, and you have beta y OM D 1 G of something from C to set. Okay. Beta y. So you see, you are moving. So this natural isomorphism move f here on the left to G on the right. F here on the left to G on the right. So this. Remark. It look like the notion of adjoint matrix or adjoint operator defined. So it's just independent remark. You don't need to care about that. So you have a matrix on a vector space. So for V vector space, or if you want, or H Hilbert space. And so for all U V in V, or Hilbert space, should not, or Hilbert space directly. Vector space for matrix and Hilbert space for operator. Or Hilbert space in infinite dimensional case. And M in the endomorphism of V, or the bounded operator, it's okay. So you define, so it's a matrix, it's a matrix. So the inner product U V, so for all U V in V, is equal to U N V. So M star. Yeah, anyway, I will don't go into the details. Just M star, where M star is the adjoint of M. So you see, this is exactly the same structure here. You move in the inner product, you move M from left to right, and then by moving that, what you get is the adjoint. And this is also the same thing here. You move F from left to right in this structure, and G is called, F is called the left adjoint of G, and G is called the right adjoint of F. So the analogy is not completely realized. You cannot realize this analogy into category easily, I guess, directly, but it's good to have that in mind, because this is what people already know from linear algebra. So F is called a left adjoint of the functor, left adjoint functor of G, and G is called the right adjoint functor of F. Okay. And so why? So as I said, what is the point of mentioning that? The point is the following exercise. Exercise. This exercise will be about the relation with the left and right dual. So exercise. Let C be a category, and C the monoidal category Yeah. The monodal category of functor from C to C. Endo functor. So you see, this is funny. In fact, here you have the analogy can go very deep because you have NC. C corresponds to the vector space. The category corresponds to the vector space. And C corresponds to the algebra of matrix. And the inner product corresponds to the offset. But at least for you have the same notation endo functor and this is endomorphism for V. So endo mean from it to itself or something like that. Okay, so so let's see the category. You take the monoidal category of functor from C to C, the endo functor. Let F. Oh, c'est quoi ça? Let Fg be two endo functor, not two objects of this monoidal category. B, so B endo functor. So the exercise is to show that F is a left adjoint functor of G. So with as the definition as above. Definition as above with D equals C. You have this subcategory. If and only if F is a left dual of G in, so left in C is a left dual of in and of C, the monoidal. Okay. And yeah. So show that. This is the exercise to show that. And of course, and idem. F is the right adjoint of the functor C if and only if F is the right dual of C. Blah blah blah. So show that maybe to show that G is the right dual of F in C if and only if G is the right dual of F in and of C. Okay. So this is the exercise, and this is the motivation for the notion of left and right dual. So the notion, so then the notion of left respectively right dual object generalize the notion of left and right adjoint functor. Okay. So this is nice because the notion of left and right adjoint functor is fundamental in category theory. So we are dealing with something generalizing this fundamental notion. Okay. So now we can state the proposition I mentioned before and prove it, at least begin to prove it. So the proposition says about the unicity et maintenant, okay, yeah, okay. Functor. I cannot write very cleanly. Short. Okay. A proposition. Proposition. I will state the proposition, I will prove it, and then I will reformulate the proof pictorially, and you will see the pictorial proof is very short and very easy. Immediate, in fact. So if X is an object of C, monoidal category, as a left, so this is the end of what I said. I had the adding part. So end of the added part. End of added part. So C now is monoidal category. So if X monoidal, C monoidal category, as a left respectively right dual object, then it is unique up to a unique isomorphism preserving the evaluation and co-evaluation morphism. Okay. Okay. So you can see this proposition as a generalization of the theorem of uniqueness of the inverse in a group. So if you have a group, the inverse is unique. So you have two inverse. But if you are in a monoid, so in a monoid in general, the notion of left inverse is not unique. It's unique if there exists a left and a right inverse. So this is a bit confusing for me, at least philosophically. because the monoidal category is supposed to be a categorification of the notion of monoid, but something is true for monoidal category, but not true for monoid. In a monoid, the left inverse is not necessarily unique. It's unique if only if there exists a right inverse. But in a monoidal category, if the left inverse exists, then it is unique up to isomorphism. But in a monoid, this isomorphism should be identity. But anyway, at least for group, it's okay. So proof of that. So let. So you take two object of X. Let E1, C1, E2, C2 be the corresponding evaluation and co-evaluation morphism. So E1, C1, the evaluation and co-evaluation for X1 star, and E2, C2, the evaluation and co-evaluation morphism for X2 star. So consider, now we want to make a morphism between X1 star and X2 star. So consider the following morphism from X1 star alpha from X1 star to X2 star. So before writing, what is the idea to get such a morphism? We know that if you compose evaluation, co-evaluation, E1, C1, then by definition, you should get an identity morphism. So you have the axiom of the evaluation, co-evaluation for that, the axiom on evaluation, co-evaluation for that. So they should check some composition should be identity, and the idea to get alpha is you mixed. So you take E1 and C2, or you take C1 and E2, and you compose like that, and then you will get a morphism from X1 star to X2 star. So the idea is the following. So defined as follow. So you have X1, E1 or C2, you will get alpha, and C1, E2, you will get another morphism called beta, and we will prove that alpha composed with beta is identity, so that it's an isomorphism. So consider the following morphism. So X1 star, and then, so again, this is X1 star tensor 1. 2. So you apply identity of X1 star. Here you apply C2. So X1 star tensor X tensor X2 star. And then you apply the associativity constraint inverse. X1 star tensor X tensor X2 star. And you apply first C2 and then E1. E1 identity of X2 star. And you go to X2 star. So this is very, so again, this is like that. So again, similarly, you use C1 and E2, and you get beta. Similarly, consider beta from x2 star to x1 star by using C1 and E2 instead of C2 and E1. And we will show that alpha composed with beta and beta composed with alpha are identity morphism. So that alpha is isomorphism. And then we will prove that alpha preserves the evaluation coevaluation and is the unique one preserving. Okay, so how to show? So as I said, there is a quite trivial pictorial proof of that. But first, let's write the formal proof. And the formal proof, in fact, so in the pictorial proof, we will see we need to do some move, some topological move in the picture. And so this formal proof, in some sense, proves that it's allowed. It's allowed to make such a move. So consider, but in general, so you prove one time you can make some move, and then you can use this move. But in the book, they don't consider pictorial proofs. Anyway, so consider the following diagram. Where the associativity constraints are suppressed. Associativity constraint and parenthesis ok. Juste maintenant? C'était juste maintenant. Ok. So we will consider a diagram and we will not put the parenthesis and the associativity constraint. As we said, as we see with McLean coherence theorem, we don't need to care about that. The associativity constraint and parenthesis are suppressed. Yeah. So you start by by coherence theorem. Okay, so you start from X star. So the idea is to compose alpha beta and beta alpha. So you start from X1 star, and then you apply what? You apply alpha. So alpha, you have the identity tensor C2. So identity of X1. So I don't write also the identity of something. Then you have X1 star tensor X tensor X2 star. So to be usually you should write something like that to be without convention and without, yeah, this is also a convention, in fact. You can suppress, this is another convention. Convention to also a convention. So without convention, you should put 1 here, you should put parentheses here, etc. But we don't put 1, we don't put parentheses. There is no, at least for this diagram, there is no confusion possible. And then you apply E1 tensor identity, E1 for that, and you get x2 star. So this is alpha. And then you apply beta. So beta is like that. So I will need some place. So identity tensor C1, x2 star tensor x, tensor x1 star, and then E2 tensor identity, x1 star. So this is alpha and beta. So this is alpha, this is beta. We want to show this is identity. So we need to decompose this. We need to make. So what we can do? So we can go from here to here. Here you apply. So you apply identity tensor C1 from this step, and you get so x1 star x tensor x2 star tensor x tensor x1 star 1 star. Okay, so C1, where is C1 here? C1 is here. Which C1? So if I'm not mistaken, okay. So what I said, C1. So the co-evaluation map is XX star, 1 to XX star. So C1 is this one. There's C1 here. Applied, you have tensor 1 here, and you have so there is no confusion possible. Ouais. Pas d'image. Il y a 4 minutes, il n'y a pas d'image. Ah oui, je me suis pas remis dans la... Sorry. My connection was out. So now it should be okay. No, c'est bon? So when should I? So I should restart from where? Je sais plus parce que j'en ai. Okay, so I will. So the proposition. So I will reread from here. So we will show that if an object has a left or right dual object, then it is unique up to the unique isomorphism. Okay. So you take 2, assume you have 2, x1 star, x2 star. And these are the evaluation and co-evaluation for x1 star, this evaluation correlation for x2 star. You can make a morphism from x1 star to x2 star by combining E1 C2 or C1 E2 instead of just taking E1 C1. This makes the identity. So for going from x1 star to x2 star, you mix the two. So here you will C2 E1, and you get a map from x1 star to x2 star. And you can similarly use C1 E2, and you get this map. Okay. And so we want to show these two maps are identity morphism to get that alpha is an isomorphism. So we want beta composed with alpha to be identity. So we want, this is alpha, this is beta, and we want this composition to be identity. So we will put some intermediate object. So you apply identity tensor C1 at this level, and then you come back, you apply E1 tensor identity. So maybe the identity are not the same, but there is no confusion possible. So, okay. And you come back here. Here the E1 should be, here the E1 should be applied to that. Anyway. Okay. And here you apply E2. So identity tensor E2 tensor identity. And the E2, so evaluation map, as I said, is x star tensor x to 1. So there is no choice. The E2 should be applied to that. It cannot be applied to that because evaluation is x star tensor x to 1. So this, you cannot apply evaluation to this one. It should be this one. Okay. And what you get is x1 star tensor x tensor x1 star. And from here, you also apply identity tensor C1, and you get x1 star tensor x tensor x1 star. Here, you just apply the identity. And here, you apply identity tensor C2 tensor identity. And C2, so C2 co-evaluation is x tensor x2 star. So the C2 corresponds to this one, this part. No choice. And finally, this part is E1 tensor identity. And again, E1 corresponds to x1 star x. So you apply E1 to that. Okay. So we want to show this diagram commute. And again, we need. Okay. So we will decompose the proof of the commutation of this big diagram in two parts. So you have 1, 2, 3, 4. What about 1? So what about 1? So let us show that the local diagram 1, 2, 3, 4 commute. So what about 1? So one. Ça reste combien de temps? Il reste 4 minutes. Wow. Okay. So we have no time to finish the proof. So I will first mention so what about one? One. So formally, I will prove one formally, and then I will show what is a move. So, but I have no time. So formally, first. So you start from X. Well, I have no time. No time, so I will show maybe the picture. So the picture and tomorrow we will see formally. So picture, you have that X1 star, and you have something like that and something like that, and here you have C2, here C1, and this is equal to, you have again that, and you have first like that, C2, C1. So the proof is that, so this is equal. The proof is that it is allowed to make such move. So you can make this move and make this move. And this will, so you have one way and the other way. One way is this one, and the other way is this one. And these two are the same. So you can prove it formally. This is direct, but you can see pictorially. This is just this move. You just put that here and this here. This is small topological move. So we will see. We will see the formal proof tomorrow. And it's okay for today. So tomorrow we will restart from here. I will need to redraw this big picture. Anyway, it's like that. So we can stop here. See you tomorrow. And sorry for the disconnection.